In this video, I want to discuss the choice of m in the Lagrange Error Bound formula. If you aren't familiar with all the notations in this formula, you should watch my Lagrange Error Bound Part 1 video. If you don't know where this formula comes from, you should watch my Lagrange Error Bound Part 2 video. Just a quick recap, A is the center of the Taylor series, so sometimes people also use the notation C or x sub 0. Sometimes instead of putting the absolute value around x minus a, people just put the absolute value around the whole thing on the right side instead. N is the degree of the Taylor polynomial. So for the m here, sometimes people use k sub n+1 instead of m. They stand for an upper bound for the n+1th derivative of f on the interval between x and a. So x is the x value that you're interested in, is the x value at which you are approximating your function, and again, a is the center. So sometimes the value of x could be less than a, so in this case, my inequality here will just become x is less than or equal to z is less than or equal to a. So here, our k sub n+1 or m is an upper bound of the absolute value of the n+1th derivative of f, which means the value that you pick for m, or k sub n+1, should be a number that is greater than or equal to what I just wrote down in gray here. Finding the maximum of absolute value of the n+1's derivative could be tricky. Sometimes you know exactly what that value is, so you can just simply use that value for your m. Sometimes even if you know what the maximum value is, you still cannot use that number, maybe because that number is not a good choice. And sometimes you may not even know what the maximum value is. So for example, if the n+1th derivative of your f of x is equal to sine x on the interval between 0 and 1.5. So sine is a periodic function. It's neither always increasing nor always decreasing. And for x values that are between 0 and 1.5, we may not even know whether your sine x has reached its maximum or minimum yet. So in this case, we don't know exactly what the maximum is, but we know that sine x is bounded between -1 and 1. So 1 would just simply be a really good choice for m. So let's look at an example here. We are trying to find an upper bound for the absolute value of the error made in approximating the value of e squared using the 6th degree Maclaurin polynomial for f of x equals e to the x. So this means we want to approximate f of x for x equals 2. We're using a 6th degree polynomial, which means our n is equal to 6. So n+1 is 7. Maclaurin polynomial is the same as Taylor polynomial centered at 0, so that's telling us that a is equal to 0. If you're taking the AP Calculus BC exam, you don't usually see the notation absolute value of error. Instead, you see this notation quite often. The absolute value of the difference between f of 2, that's the actual value of the function at 2, and p sub 6 of 2, that's the approximated value at x equals 2 using the 6th degree Maclaurin polynomial. Now we're going to find the 7th derivative of f of x, which in this case is just e to the x. We know that e to the x is always positive and it is always an increasing function. This means that to find the maximum of the absolute value of the 7th derivative of f of x, for x values between 0 and 2, all you have to do is to plug in 2 for x. So that means that this maximum value that we're looking for here is equal to e squared. But hey, we cannot use e squared in our error-bound formula. Why? Well, because we were trying to approximate e squared to start with. If we know what e squared is, there really isn't a point of doing this approximation. If we don't know what e squared is, it really doesn't make sense for us to use what we're trying to approximate its own error bound. Another way to look at this is that if you're trying to approximate the value of e squared using a 6-degree Taylor polynomial, then this could only mean two things. One, that means that you don't have a calculator with the e key on it, so that's why you have to do the approximation. Or this could mean that you're taking a test or doing your homework where your teacher is asking you to do the approximation. Even if this is the case, what you're doing should still make sense, right? So the underlying assumption should still be that, hey, you don't have a calculator that has the e key on it. So we should find a nice number, probably an integer, that is close to the value of e squared and is also greater than or equal to e squared. This requires you to at least have some prior knowledge about e, so you should at least know that, oh, e is about 2.7 something. Or at least you should know that e is a number that is bounded between 2 and 3. So this tells us that e squared is bounded above by 3 squared, that is equal to 9. So some of you might want to be more accurate. You might be wondering, well, can we use 2.8 squared instead of 3 squared? If you're willing in this case to square decimals and do divisions with decimals in it, I'd say sure, but you really shouldn't need to torture yourself this way, so 3 squared should be good enough. But now maybe someone else wants to ask, well, since we want to choose a nice number, can we use 10 instead of 9? True that 10 is an even nicer number and it is still a decent upper bound. But to me, 9 is already a good number, and using 9 will give us a more accurate error bound. So I am actually gonna stick with 9 here. So now we should have all the information that we need to plug them into our error bound inequality. And the value here should be easy enough to evaluate even without the calculator. 2 to the 7th is 128 times 9, that's 1,152, and 7 factorial is 5,040. Divide the two numbers, we get approximately 0.229. And for comparison purpose, here is a table with the 3 m values that we have mentioned in this video, together with the corresponding upper bound of the error that you would find by using each m value. All three answers are correct there. 0.199 is an upper bound of the error in approximating e squared using the 6-degree Maclaurin polynomial. It actually gives us a pretty accurate interval by telling us that, hey, the error is at most 0.199. However, when you have to solve problems like this, it may not be possible nor necessary to use numbers like 2.8 squared. That actually makes 3 squared a really good candidate for m, probably the best candidate in this case. So if the calculation is possible, you still want your m to be as accurate as possible. For example, if I ask you in this case to show that the error is at most 0.25, so as you can see here, in this case, if you use 10 instead of 9, you would not be able to show that. Also, if you're approximating something using the Taylor polynomial, you might be wondering, well, really how many terms must I use in order for the error to be within, say, 0.25? So if you use 3 squared for m, you will see that, oh, the 6th-degree polynomial is enough. You really don't need another term, but if you use 10 for m, you will think that you do. Another example, everything else is the same except instead of e squared, we are approximating e to the 3/2 now. All the steps are pretty similar. Except when you get here. So we're still using 3 instead of e. So we have 3 to the 3/2 as our m value this time. If you use 3 to the 3/2 as your m value, most teachers, including myself, actually probably will be satisfied with your answer. But really, now if you think about it, is this the best choice? It really now depends on our assumption of which technology is available to us. So if you are approximating e to the 3/2, again, most likely you don't have a calculator with the e key. And if it doesn't have an e key, there is a chance that it cannot do the exponent of 3/2 either. So 3 to the 3/2 is equal to 3 to an exponent of 1/2, and then raised to the third power, which is equivalent to square root 3 to the third power. Again, if your assumption is that your calculator can do square root, then great, you can use 3 to the 3/2, no problem with that. But if your calculator can't calculate square roots, or if you assume that you don't even have a calculator to use, 4 is slightly bigger than 3 and it's also a perfect square number, so it probably makes more sense in this case to use square root of 4 cubed, which is equal to 8. On the other hand, if you are worried that 4 is too far away from 3, and if you want your answer to be more accurate than that, you may know that square root 3 is about 1.732. So if you are willing to accept more trouble in your calculation, you might want to use 1.8 cubed, which is the same as 9/5 cubed, as the value of m. Again, here's a chart for comparison. So here you can see if we use 8 as our m, the upper bound of the error that we will get is 0.0271, which is really a small number already, but at the same time, this number is also over 50% bigger than 0.0176. Do you think it's acceptable to use 8? I guess there's no right or wrong answer here, but there definitely is an answer that I prefer. So what do you think? That was all. I hope this video was helpful. See you next time. Bye bye.